Hello everyone, welcome to Organic Chemistry 1. For this chapter, Alkynes, the first part is always introductions. We'll talk about structure, a little bit of namings and synthesis. And then the second part will be reactions, okay? And then we also need to talk a little bit about spectroscopy, but so far there's only IR, so it should not be it should not take too long. Okay. So let's start out with structure. Okay, as you know, alkynes has triple bonds. The simplest alkyne has one triple bonds, and so that's put us 2 degree of unsaturations, and one double bond is consists of a single bond, the first bond, which is the sigma bond, and you have 2 pi bonds, and 2 pi bond make it 2 degree of unsaturations. So that means we are short 4 hydrogens. So instead of Cn H2n plus 2 for saturated alkanes, we have -2. So that's the formula, CnH2n plus -2. Okay, if n equal to 2, of course you have to have at least 2 carbons. If you have 1 carbon, it won't work. That means you don't have any hydrogens. Okay, so you have 2 carbons, and that put you 2 times 2, that's 4 minus 2, so that's C2H2. That's acetylene. That's the simplest alkene you can have. All right. In terms of nomenclature, very similar to alkene, this is alkyne, so the ending is IYNE. All right, so you notice that. Now, the way you numbers is lowest numbers possible. Okay, so in this case, obviously, you go from right to left. 1, 2, 3, 4, 5. So that's a pent. That's a 5. So that's a 2 pentyl. And you can also call it pen-2 YNE. Okay, so pen-2I. Okay, that will work as well, but this one flows a lot better. Now, if you have substituents, okay, you still have to go with the lowest number for the alkyne. That's the most important functional group in this compound. So let's say if you go from right to left, 1, 2, 3, 4. Okay, so you start the triple bond with number 4. If you go from left to right, it will be 1, 2, 3. So that's better. So therefore, we have to go from left to right. So imagine 1, 2, 3, 4, 5, 6, 7. So I suggest you to write on a piece of paper and number them yourself. Okay, that's the easiest way. Okay, if you're really good at this, you can imagine that, you can have that in your mind. But if you want to see a visual persons, you want to see, it's best if you write it down on a piece of paper. Okay, so 1, 2, 3, keep that in mind. 4, 5, 6, 7. 7 is a hept, so it's a heptine. So that's gonna be 1, 2, 3, 4, 5, 6. So bromo go first, because alphabetical order, bromine go first. So that's 6 bromo, 2 methyl, that's it. And then 3 heptide, okay? And so on and so forth. Now, and the same thing for here. With OCH3, we call that a methoxy. So here we still go from left to right. 1, 2, that's closer. 3, 4, 5, 6. You get that? So that's why it's 4 methoxy hexine. And then finally, this one is very interesting. You have 2 functional groups. You have a double bond and a triple bond. Okay. Now, a double bond actually has higher priority than the triple bond, because a double bond can possibly have cis or trans. Okay, if it's internal. All right, not in this case. Okay, so in this case, so you call this number 1. Okay, that's 1 instead of that. 1, 2, 3, 4, 5. So that make it a 2 methyl 1 pentene 3I. Okay, or you can split. Okay, you can split 2 methyl pent 1 in 3I. Okay, and that's one way to do it. All right, and then if you have alcohol with we're gonna have a whole chapters, with alcohol. The next chapters, that's gonna be alcohol. So in this case, we have 1, 2, 3, 4. We can treat the OH as a substituent if we want. Okay, that's one way. So that will be 1, 2, 3. So that's why we call it 3-hydroxy. OH is called hydroxy, and 1-butyl. Or OH actually has higher priority than alkyne because oxygen has higher oxidation numbers. I mean the electronegativity. Or you can also think about OH has higher oxidation states. Okay, that carbon has higher oxidation states because oxygen is more negative again. So you go 1, 2, 3, 4. Okay, so in that case, that put us on the alkyne will be number 3. So there's 3-butyl 2O. Okay, so that's one way, more like in favor of alcohol, or the second way is in favor of alkynes. Okay, so the carbonyl alkyne is a triple bond, so it's sp. Okay, it's linear molecular shape, or sp. All right, so that's a little bit of naming, and I'm going to go through the molecular orbital real quick. As I mentioned earlier, a triple bond consists of a sigma bond and 2 pi bond. You can see right there 2 pairs of p orbital, ones going up and down like this. Okay, so you see same colors overlap. Okay, the other one is the one that goes sideways, the white and black. Okay, like that. So so you have two set of p orbital overlap that make it a 2 pi bonds. All right. Now, in terms of chemical properties, now alkyne compared to inorganic acid like HCl or nitric acid, HNO3, and this is nothing compared to that. Okay, but inorganic chemistry is pretty reasonable in terms of acidity. Okay, compared to alkane or alkene. With a pKa, alkyne has a pKa of 25. We're talking about the terminal alkyne, that's the one with the hydrogens. When we talk about pKa or acidity, we talk about that hydrogens, removing that hydrogens. Okay, that's what we're talking about. How easy it is. Okay, so the smaller the pKa, the easier for that hydrogen to be off. Okay, so 25 is not that acidic. Okay, but compared to alkanes, it's not bad. All right, so that means we need a strong base to remove that hydrogens. And once we remove the hydrogen, this C becomes C minus. That's a conjugate base. Remember, the weaker the acid, the stronger the conjugate base. So this one's going to be strong enough to be a good nucleophile. Okay, and that's what we're going to be taking advantage, okay, of. Now notice that the ammonia has a pKa of 35, so the conjugate base of ammonia will be a good base, okay, for that. Not the alcohol. Alcohol is more acidic, so it won't work. All right. Okay, here we go. So we're going to use the conjugate base of ammonia, which is amine. Sodium amine is a good base, and it will take that hydrogen to become. So here the byproduct here will be ammonia, NH3, and it will take that hydrogen, leaving us with the C minus. That's we call alkynium ion, and sodium plus. So your byproduct is going to be NH3, and it will evaporate from the solutions. Obviously, if you have the internal alkyne, you don't have any hydrogen in here to eliminate. Okay, not out here. It's not going to take the hydrogen here, only from the C of the triple bond. Okay, that's why you can't make any negative ion there. All right. Now the reason why we need that, because we're gonna go on and use that for the synthesis of alkynes. Okay. Now because of the reaction of the terminal alkyne, because of the hydrogens, we can test. So we can test for terminal alkyne, which means the triple bond at carbon number 1. So we can test that with various substances like copper nitrate. It will react, okay. It will remove that hydrogens. It will react with silver nitrate, okay, because it acts like an acid. And also when you get the compound, you can always put the hydrogen back in with under acidic condition to put the hydrogen back in. Okay. All right. So with those, you can test, and the precipitate formation will tell us that is a terminal alkyne. Okay. All right. So keep that in mind. We're gonna make that minus right there. So to make alkyne, we either do elimination, just like alkene. If you remember alkene, you make alkene the double bond, you do 1 eliminations. Now you want a triple bond, that's 2 degrees of saturation. You either do 2 eliminations, okay? Or in this case, it's really nice. You use 1 alkyne, you make another alkyne, okay? In this case, for example, you use a terminal alkyne. Again, this reaction we see previously, okay? We use a strong base, sodium amine, to remove the hydrogen to make the alkynium ion, and then we run an SN2 reactions. So to make the alkyne longer carbon chains. All right. So obviously you do an SN2 reaction, so you want to pick the alkyl halide that is primary. Okay. Now secondary is sometimes okay, but most of the time it's gonna do the elimination. So you you will get the double bond instead. Okay, so you always stick with primary to make sure you get a good SN2 reaction instead of elimination. You can see right here, this is eliminations, and that's your product, and you get back your alkyne. So that's not what we want. All right. Now there's other reaction as well, and like a ketone or aldehyde, because when you have a nucleophile, it can pretty much react with any carbon that's positive. So in this case, the C double bond O, the carbon is positive because oxygen is more electronegative. So it's going to be added on to that, and then you get the alkoxide O minus, which easily be protonated. You know, take a hydrogen from acid or protonated water, and then to get to alcohol. So you start out with an alkyne, and you end up with an alkyne with another functional group, which is the primary alcohol. Okay, and that's if you want to make a multifunctional group, this is the way. And then here's more example for you. With acetone, you get a secondary alcohol. With a ketone, you get a tertiary alcohol. So it's really a powerful reactions where we just have to pick the coupling, the electrophile, okay, where we're going to connect either formaldehyde and an aldehyde or a ketone. This is acetone, sorry. Okay, that's not acetaldehyde. This is acetone. So we can customize the add-on reagent to make whatever we want to, from primary to tertiary alcohol. Well, as I mentioned earlier, you can do synthesis of alkene by elimination. Now alkyne, you do double eliminations. Okay, so that's going to be the same principle here. If you do 1 elimination, you get a double bond. You do another eliminations, okay, so you got to have 2 vicinal, meaning close by, halogens, okay. Or you can have the 2 halogen on the same carbon, which is called germinal dihalide. X here can be chloro or bromo, or even iodo. Okay, here's an example. Bromine is the most popular one, and you can do double elimination. So you're going to have a strong base, KOH, at 200 degrees Celsius, because heat will favor eliminations. So two elimination will give us the triple bond. Okay, the first elimination, remember, give us the double bond, and then mechanisms all here. Okay, eliminate the hydrogen, make the double bond, kick the halogen out. And remember, X, most of the time we're going to be using Br. Okay, Cl is possible, iodide is possible too. All right, that is two main way to do it. So you start out with an alkyne, you make another alkyne, or you start out with a dihalide and you make an alkyne. Okay, so that's one way. The and here the another example here for you to see when you can make an alkyne using a strong base for eliminations here. All right, but these are the main one. Okay, we can skip this part in the bottom here, but double eliminations and through alkynium ion, it's good enough. All right, so and we have a few practice problem, and so you want to check it out, and from nomenclature to synthesis. Okay, taking advantage of those. So there's only two main way to do that. Okay, in the next video we're going to be looking at the reactions of alkyne, what we can do with it. Okay, so that first part was nomenclature and synthesis, and like I said, there's only two way. Okay, double eliminations and using another alkyne. Okay, we'll continue in the next video on reaction of alkyne. Thank you.